Hello, and thank you for joining me on this journey beyond the familiar edges of our solar system. Tonight, we will slowly drift into a state of ease and explore the distant realm of dwarf planets, small ancient worlds like Pluto, Ceres, Eris, Haumea, moving through cold sunlight far from the warmth of the inner planets. Here, frozen landscapes stretch beneath endless stars, underground oceans rest beneath thick shells of ice, and fragile atmospheres appear and disappear as these bodies follow long, resonant paths through the Kuiper Belt. These worlds carry the marks of ancient collisions and preserve chemistry unchanged for billions of years, acting as time capsules from the earliest days of planetary formation. As you picture their slow rotations and vast distances, allow curiosity to soften and thoughts to slow. If you enjoy these relaxing moments, please consider leaving a like, subscribing, or sharing your thoughts below. Your support is deeply appreciated and helps others find their way to this peaceful space. You can also turn on the notifications so you don't miss any of our future journeys together. But for now, just breathe. Let your body relax, release any tension, and allow your mind to drift. Let's begin. Dwarf planets occupy a strange middle ground in planetary science, defined not by size alone, but by behavior. They orbit the Sun directly and possess enough mass for gravity to shape them into rounded forms, yet they lack the ability to clear their orbital neighborhoods. This definition, adopted in 2006, reshaped humanity's map of the solar system and forced scientists to reconsider how planets form, evolve, and interact. Rather than being failed planets, dwarf planets are now understood as preserved building blocks from an earlier cosmic era. Pluto, the most famous dwarf planet, follows an orbit that is both steeply tilted and highly elongated, carrying it from inside Neptune's path to far beyond it. During part of its 248-year journey, Pluto receives more sunlight than Neptune does, causing its surface ices to sublimate and form a temporary atmosphere. As it recedes again, that atmosphere collapses and freezes back onto the surface, turning Pluto into a world that breathes on astronomical timescales. Beneath Pluto's frozen exterior lies evidence of unexpected internal activity. Data from NASA's New Horizons mission revealed vast nitrogen glaciers, fractured water ice mountains, and plains with almost no impact craters. These features suggest geological renewal driven by internal heat, possibly aided by radioactive decay. Some models indicate a subsurface ocean insulated beneath layers of ice, challenging the assumption that small worlds cool quickly and become inert. Charon, Pluto's largest moon, is so massive relative to its parent that the two bodies orbit a shared center of gravity located outside Pluto itself. This makes the Pluto-Charon system more like a binary world than a planet and satellite. Charon displays deep canyons, frozen lava flows, and evidence of early internal expansion, hinting that even moons of dwarf planets can experience complex geological histories shaped by heat and ancient chemistry. Ceres, the largest object in the asteroid belt, stands apart from its rocky neighbors. Unlike typical asteroids, Ceres contains significant amounts of water ice and hydrated minerals. Bright spots within its craters, especially in a crater, consist largely of sodium carbonate deposits left behind by briny liquids that once reached the surface. These findings suggest that Ceres remains chemically active long after its formation. The Dawn spacecraft revealed that Ceres likely harbors a muddy mantle rather than a solid rocky one. its interior may resemble a frozen slurry where salts prevent water from freezing completely. This structure allows cryovolcanism, a process in which salty water erupts instead of molten rock. The lonely mountain Ahuna Mons appears to be the remnant of such an eruption, rising abruptly from the surrounding plains like a scar from deep time. Eris, slightly smaller than Pluto but more massive, was instrumental in redefining what a planet is. Its discovery forced astronomers to confront the fact that many Pluto-sized objects exist in the outer solar system. Eris follows an extremely distant orbit, spending centuries in deep cold before slowly returning toward the Sun. Its surface reflects nearly all incoming light, suggesting a coating of fresh, frozen methane. Haumea challenges expectations through its extreme shape and speed. It spins once every 4 hours, so rapidly that it stretches into an elongated ellipsoid rather than a sphere. This rotation likely resulted from a massive collision early in its history. Fragments from that impact now form a family of objects with similar orbits and compositions, offering rare evidence of a large-scale collision preserved across billions of years. Haumea also possesses a ring, making it the first dwarf planet known to have one. The ring's discovery revealed that even relatively small bodies can host stable ring systems under the right gravitational conditions. Its presence suggests a dynamic environment shaped by past impacts and ongoing orbital interactions, reinforcing the idea that dwarf planets are not static remnants, but evolving worlds. Many dwarf planets reside in the Kuiper Belt, a vast region beyond Neptune filled with icy debris. This region acts as a fossil record of planetary formation, preserving materials largely unchanged. Since the solar system's infancy, studying dwarf planets within the Kuiper Belt allows scientists to test models of how giant planets migrated and reshaped the outer solar system through gravitational scattering. Orbital resonances play a critical role in dwarf planet survival. Pluto, for example, is locked in a 3-to-2 resonance with Neptune, completing 2 orbits for every 3 of Neptune's. This resonance prevents close encounters despite their crossing paths, creating a gravitational rhythm that has remained stable for billions of years and protected Pluto from ejection or collision. Surface temperatures on dwarf planets can plunge below -220 degrees Celsius. Yet chemistry continues even in this deep cold. Radiation from the sun and cosmic sources triggers reactions among frozen methane, nitrogen, and carbon monoxide, producing complex organics known as tholins. These compounds stain surfaces with reds and browns, creating vivid planetary landscapes sculpted by invisible energy. Some dwarf planets may contain more water than Earth, locked beneath thick shells of ice. Because water ice behaves like rock at extreme cold, it can support towering mountains and deep fractures. This unusual mechanical behavior reshapes assumptions about geology, showing that solid ice can play the same structural role as stone on worlds far from the Sun. The boundaries between dwarf planets and large moons can blur. Objects like Triton, Neptune's captured moon, share characteristics with Kuiper Belt dwarf planets. This overlap suggests that some moons began as independent worlds before being captured, offering a glimpse into the chaotic gravitational exchanges that occurred as the giant planets settled into their current positions. Dwarf planets challenge the idea that habitability requires Earth-like conditions. Subsurface oceans insulated by ice may persist for billions of years, potentially allowing chemical complexity to develop in isolation. While sunlight is scarce, internal heat and chemical gradients could provide alternative energy sources, expanding the range of environments considered potentially life-supporting. The classification of dwarf planets remains incomplete, with many candidates awaiting confirmation. Astronomers continue to discover distant objects with spherical shapes and stable orbits, suggesting the current list represents only a fraction of what exists. Each new discovery refines statistical models of solar system architecture and deepens understanding of planetary diversity. Cultural perceptions of dwarf planets often lag behind science. Pluto's reclassification sparked widespread debate, revealing how emotionally attached people are to cosmic labels. This reaction underscores the human tendency to personalize distant worlds, transforming astronomical objects into symbols of exploration, nostalgia, and changing knowledge rather than mere data points. Future missions may target dwarf planets beyond Pluto, using advanced propulsion and compact instruments. These missions aim to sample surface composition, probe internal structures, and map unexplored terrains. Each encounter promises to reveal not just isolated facts, but broader truths about how small worlds record the solar system's earliest chapters. Taken together, dwarf planets form a hidden network of storytellers scattered across space. Their orbits, scars, and chemistry preserve information erased from larger planets by tectonics and erosion. By listening closely to these subtle worlds, scientists reconstruct events that shaped everything from Earth's oceans to the distant debris fields still circling the Sun. Far from being uniform, dwarf planets display an astonishing diversity of densities that reveal their internal makeup. Ceres is relatively lightweight, indicating a large fraction of water and hydrated minerals, while Eris is far denser, implying a greater proportion of rock and metal. These differences suggest that dwarf planets formed in varied regions of the early solar nebula, or experienced distinct thermal histories. By comparing mass, volume, and orbital location, scientists infer migration patterns of the giant planets, which scattered primordial material outward and inward, mixing icy and rocky components across vast distances. Hidden beneath thick crusts of ice, several dwarf planets may retain internal heat, generated by radioactive elements locked within their rocky cores. Even small amounts of this heat, trapped over billions of years by insulating ice layers, can maintain pockets of liquid water mixed with salts or ammonia. Such environments resist freezing at extremely low temperatures, creating long-lived reservoirs that defy earlier assumptions about small bodies cooling rapidly. These findings reshape models of thermal evolution and suggest that internal complexity is not limited to large planets. Unlike the classical planets, many dwarf planets possess chaotic axial tilts that dramatically alter their seasonal cycles. Pluto's axis is tipped more than 120 degrees, causing entire hemispheres to experience decades of continuous sunlight, followed by equally long periods of darkness. This extreme tilt drives large-scale redistribution of surface ices, carving patterns into plains and mountains that record climate shifts lasting centuries. By studying these cycles, scientists gain insight into how volatile substances behave under conditions far beyond Earth's experience. Rather than forming in isolation, some dwarf planets appear to have assembled through hierarchical accretion, gradually merging smaller icy bodies over time. This slow build-up preserved delicate chemical signatures that larger planets lost through melting and differentiation. Spectroscopic analysis reveals simple molecules alongside complex organics, frozen in place since the solar system's earliest epochs. These chemical records allow researchers to trace how carbon, nitrogen, and oxygen were distributed long before Earth became habitable. Occasionally, dwarf planets display signs of surface renewal that challenge expectations of geological stagnation. Smooth plains on Pluto and possible cryovolcanic features on Ceres lack heavy crater saturation, indicating relatively recent resurfacing. Such activity suggests internal mobility driven by heat, compositional layering, or phase changes within ice. These observations force planetary scientists to rethink the lower size limits required for ongoing geological change, expanding the range of worlds considered dynamic. Many dwarf planets are accompanied by complex satellite systems that provide clues to ancient collisions. The moons of Pluto, for example, orbit in a near-circular coplanar arrangement consistent with formation from debris following a massive impact. Studying these satellites reveals how angular momentum was redistributed and how material reaccreted under low gravity. These systems act as natural laboratories for understanding how collisions shaped not only dwarf planets, but also early Earth and the Moon. Surface gravity on dwarf planets is weak, yet it exerts a powerful influence on landscape formation. Mountains composed of water ice can rise several kilometers high because ice behaves as a rigid structural material at extremely low temperatures. At the same time, low gravity allows volatile ices to migrate easily, flowing across terrain and pooling in depressions. This combination produces landforms unlike anything found on terrestrial planets, blending solidity and mobility in unexpected ways. As dwarf planets travel along elongated orbits, their distance from the Sun can vary dramatically, altering surface conditions over time. On Pluto, increasing sunlight causes nitrogen and methane ices to sublimate, thickening the atmosphere and redistributing material globally. When sunlight fades, these gases freeze out again, reshaping the surface. These orbital-driven transformations offer a rare opportunity to observe planetary-scale climate change unfolding over predictable astronomical cycles. The Kuiper Belt hosts thousands of dwarf planet-sized objects, many of which remain undiscovered due to their faintness and distance. Advanced surveys using wide-field telescopes are steadily uncovering new candidates, refining estimates of the belt's total mass and structure. Each detection helps constrain theories about how material was distributed after the Sun's formation and how gravitational interactions sculpted the outer solar system into its present form. Chemical reactions driven by solar radiation steadily alter the surfaces of dwarf planets, creating layers of complex organic material over time. These reactions transform simple ices into darker compounds that absorb more heat, subtly influencing thermal balance. The resulting color variations across a single world can reveal its exposure history, resurfacing events, and age differences between regions. Such surface chemistry acts as a visual timeline etched into ice and stone. Some dwarf planets follow orbits that extend far beyond the Kuiper Belt into the scattered disk, where gravitational interactions with Neptune continue to reshape trajectories. These elongated paths can span thousands of astronomical units, carrying objects into deep space before drawing them back toward the Sun. Studying these orbits provides evidence for past planetary migration and offers clues about how material may have been exchanged between the inner and outer solar system. Observations indicate that dwarf planets often preserve primordial porosity within their interiors. Instead of being fully compacted, they may contain networks of voids filled with ice or frozen gases. This structure affects heat transfer, internal strength, and response to impacts. Understanding porosity helps scientists interpret density measurements accurately and predict how these worlds evolved mechanically over immense timescales. Rather than being rare anomalies, dwarf planets may represent the most common type of planetary body in the galaxy. Exoplanet surveys suggest that small, icy worlds are abundant around other stars, often forming beyond snowlines, where volatile compounds condense. Studying dwarf planets close to home therefore provides a window into the dominant planetary architecture of the universe, offering context for how typical or unusual our solar system truly is. Early solar radiation played a crucial role in shaping dwarf planet surfaces by stripping lighter elements from some bodies while leaving others relatively unchanged. Variations in size, distance, and composition determined how much atmosphere each world could retain. This selective loss explains why similar objects display strikingly different surface chemistries today, revealing a delicate balance between gravity and radiation pressure. Laboratory experiments simulating dwarf planet conditions have shown that ice mixtures can behave unpredictably under extreme cold and low pressure. These experiments support observations of slow-moving glaciers made of nitrogen or methane rather than water. By recreating such environments, scientists validate remote sensing data and refine models of surface evolution on distant icy worlds. Some dwarf planets may have experienced episodes of internal differentiation, separating into layers of rock and ice early in their history. This separation would concentrate radioactive elements in the core, sustaining heat for longer periods. Evidence for differentiation appears in gravity measurements and surface composition patterns, suggesting that even relatively small bodies can undergo complex internal restructuring. The naming conventions of dwarf planets reflect a blend of modern science and ancient mythology. Names are drawn from creation deities, underworld figures, and mythic beings associated with darkness or distance. This tradition highlights humanity's enduring tendency to frame cosmic discovery within cultural narratives, linking cutting-edge astronomy to stories passed down for millennia. Tidal interactions, though weaker than those affecting large planets, can still influence dwarf planets with sizable moons. Over long periods, these forces can alter rotational states, internal heating, and orbital configurations. In tightly bound systems, tidal effects may contribute modestly to maintaining subsurface liquids, adding another layer of complexity to their thermal evolution. Remote sensing techniques such as stellar occultations allow scientists to probe dwarf planet atmospheres and sizes with remarkable precision. When a distant star passes behind a dwarf planet, subtle changes in starlight reveal atmospheric composition, pressure, and temperature. These fleeting events provide critical data that cannot be obtained through imaging alone, enhancing understanding of worlds billions of kilometers away. Ultimately, dwarf planets serve as archives of cosmic history, preserving conditions that existed before planets like Earth became geologically active. Their untouched surfaces, ancient interiors, and stable orbits offer rare access to the solar system's formative era. By piecing together evidence from these small worlds, scientists reconstruct a narrative that spans from the birth of the Sun to the dynamic planetary system observed today. Long before telescopes existed, the material that would become dwarf planets condensed from the cold outskirts of the solar nebula, where volatile compounds could solidify easily. In these distant regions, slow accumulation allowed ices, dust, and rock to bind together without intense heating. This preserved fragile molecular structures that were erased closer to the Sun. Modern analysis of dwarf planet composition therefore provides direct evidence of the chemical environment present during the solar system's earliest stages, offering insight into how temperature gradients influenced planetary diversity. In contrast to terrestrial worlds, impact craters on dwarf planets can behave in unexpected ways due to low gravity and icy crusts. Rather than forming sharp, permanent scars, some craters gradually relax as ice slowly flows, softening their outlines over time. This viscous behavior allows scientists to estimate surface ages by examining crater shapes instead of merely counting them. The resulting landscapes appear smoother and younger than their true age, revealing a slow but persistent reshaping driven by material properties rather than tectonic forces. Occasionally, dwarf planets exhibit color patterns that stretch across entire hemispheres, hinting at global redistribution of surface materials. These patterns arise when sunlight drives sublimation in one region, while colder areas trap redeposited frost. Over centuries, this cycle paints large-scale contrasts visible from millions of kilometers away. Such color asymmetry records long-term climate behavior and axial orientation, allowing astronomers to infer rotational history and seasonal extremes without direct sampling. Unexpectedly strong magnetic signatures have been proposed for some dwarf planets, based on subtle interactions with solar wind particles. If confirmed, these signatures would imply the presence of conductive layers beneath the surface, such as salty subsurface oceans. Even a weak magnetic field could influence how charged particles interact with surface materials, affecting radiation exposure and surface chemistry. This possibility broadens the scope of geophysical activity once thought exclusive to much larger planetary bodies. Beyond their scientific value, dwarf planets play a critical role in stabilizing distant regions of the solar system. Their collective mass influences the distribution of smaller debris, shaping the structure of the Kuiper belt and scattered disk. Gravitational interactions between these bodies help maintain orbital spacing and reduce chaotic collisions. This quiet architectural role ensures that the outer solar system remains dynamically coherent across billions of years. Some dwarf planets display evidence of ancient fractures that span hundreds of kilometers, cutting across plains and highlands alike. These fractures likely formed when internal layers expanded or contracted due to temperature changes or phase transitions within ice. Mapping these features allows researchers to reconstruct internal stress histories and determine whether a world cooled uniformly or unevenly. Such tectonic clues provide a rare glimpse into internal evolution without drilling or direct exploration. Unlike rocky planets, dwarf planets can experience surface renewal through the slow extrusion of volatile rich material that spreads outward before freezing. This creates smooth deposits, distinct from impact-related features. Because these flows are driven by internal composition Rather than high heat, they operate under conditions previously assumed too cold for activity. Their presence confirms that geological expression depends as much on chemistry as on temperature. The reflectivity of dwarf planet surfaces varies widely, influencing how much solar energy they absorb. Bright, icy regions reflect most incoming light, keeping temperatures low, while darker areas absorb heat and encourage sublimation. This feedback can amplify surface contrasts over time, reinforcing regional differences. Studying these reflectivity patterns helps scientists model energy balance and predict how surfaces respond to changing orbital positions. Certain dwarf planets possess moons with surprisingly similar compositions, suggesting they formed from shared material rather than independent capture. This similarity supports collision-based origin theories, where debris from a single event coalesced into multiple bodies. By comparing surface spectra of these systems, researchers can trace the aftermath of ancient impacts that reshaped entire worlds without destroying them. Far-reaching gravitational interactions occasionally shift dwarf planet orbits over immense timescales, subtly altering their distance from the Sun. These changes can expose surfaces to new thermal regimes, triggering redistribution of frozen compounds. Such orbital evolution leaves chemical fingerprints that persist long after the original shift occurred. Reading these signatures allows astronomers to reconstruct past orbital pathways with surprising precision. One overlooked aspect of dwarf planets involves their contribution to meteoritic material reaching the inner solar system. Collisions among distant icy bodies can eject fragments inward, some of which eventually intersect Earth's orbit. Analysis of certain carbon-rich meteorites suggests an origin consistent with outer solar system material, linking dwarf planets indirectly to the delivery of volatiles to early Earth. Advances in infrared spectroscopy have revealed that dwarf planet surfaces often contain ammonia-bearing compounds. Ammonia acts as an antifreeze, lowering the melting point of water and enabling subsurface liquids to persist longer. Its detection strengthens arguments for internal mobility and chemical complexity. These compounds also offer clues about the primordial inventory of nitrogen in the outer solar system. In many cases, dwarf planets rotate in a state known as non-principal axis rotation during early history, wobbling before settling into stable spins. Evidence of this behavior can be inferred from surface asymmetries and distribution of impact features. Stabilization over time reflects internal mass redistribution and energy dissipation, providing indirect information about interior structure and rigidity. Although distant, dwarf planets are not immune to solar influence. Variations in solar output across millennia can alter surface chemistry by changing radiation exposure. These subtle shifts accumulate, modifying molecular bonds and coloration. Tracking such effects allows scientists to correlate solar history with observable changes on remote worlds, extending solar science far beyond Earth's vicinity. Some dwarf planets may harbor layered atmospheres during peak warming periods, with heavier gases concentrated near the surface. This stratification affects how energy is retained and lost, influencing surface temperature distribution. Even temporary atmospheric layering leaves traces in frost patterns and erosion features, acting as a record of past atmospheric behavior. Distinctive albedo markings on dwarf planets often align with topographic lows, indicating preferential accumulation of volatile ices. These basins act as cold traps, collecting material over long durations. Mapping their distribution reveals how gravity and terrain guide surface evolution, producing landscapes governed by accumulation rather than erosion. At extreme distances, sunlight becomes so weak that even minor changes in reflectivity significantly affect surface conditions. This sensitivity makes dwarf planets excellent test cases for studying energy balance under low insolation environments. Insights gained from these worlds inform models applied to distant exoplanets orbiting faint stars. Rather than being static relics, dwarf planets interact continuously with surrounding debris through micrometeoroid impacts. These impacts garden the surface, exposing fresh material and burying older layers. Over millions of years, this slow turnover refreshes spectral signatures and complicates age estimates, requiring nuanced interpretation of surface data. Evidence suggests that some dwarf planets formed in regions later disrupted by planetary migration, relocating them far from their birthplaces. Their current positions therefore reflect a dynamic past, rather than original formation zones. By tracing compositional differences, scientists infer migration pathways that reshaped the solar system's outer architecture. Ultimately, dwarf planets embody a balance between simplicity and complexity, retaining primordial traits while exhibiting unexpected dynamism. Their study bridges gaps between asteroids, planets, and moons, revealing continuity rather than strict categories. Each discovery adds depth to the understanding of planetary systems, emphasizing that even small worlds can hold outsized significance in cosmic history. Carved into the surfaces of several dwarf planets are patterns that resemble frozen seas, formed not from water alone, but from mixtures of nitrogen, methane, and carbon monoxide. These volatile planes behave like slow-moving ice sheets, creeping under their own weight across basins. Their motion erases impact marks and piles material against natural barriers, creating ridges and cellular textures visible from orbit. Such features demonstrate that even at extreme cold, solid substances can migrate on planetary scales, reshaping terrain over millions of years. Across the outer solar system, dwarf planets exhibit striking differences in surface age, despite similar formation times. Some appear heavily cratered, preserving scars from the earliest bombardment era, while others look comparatively fresh. This disparity reflects variations in internal composition, orbital history, and exposure to resurfacing events. By comparing crater populations and terrain sharpness, scientists establish relative timelines that reveal which worlds remained dormant and which underwent episodes of renewal long after formation. Encased within thick shells of ice, pressure increases rapidly with depth on dwarf planets, altering how materials behave. Under sufficient pressure, water ice can adopt exotic crystalline forms denser than liquid water. These high-pressure phases influence internal layering and heat transfer, potentially trapping warmer material below. Understanding these phases is essential for modeling interior structure, as they affect everything from subsurface ocean stability to the way seismic energy might travel through these distant worlds. Rather than forming smooth spheres, some dwarf planets display irregular outlines shaped by rotational forces and ancient impacts. Haumea's elongated form exemplifies how rapid spin can overpower gravity's tendency toward roundness. This distortion affects surface gravity distribution, influencing where loose material settles and how fractures propagate. Studying these shapes allows scientists to infer rotation rates and internal strength, offering clues about early angular momentum and collisional history. Embedded within dwarf planet surfaces are compounds that predate the Sun itself. Isotopic ratios measured remotely suggest that some ices originated in the interstellar medium before solar system formation. These materials survived collapse of the solar nebula and incorporation into planetary bodies. Their preservation provides rare physical evidence of pre-solar chemistry, linking dwarf planets directly to molecular clouds that existed long before Earth was assembled. Observations during stellar occultations have revealed that some dwarf planets generate hazes composed of complex hydrocarbons when sunlight interacts with atmospheric gases. These hazes settle slowly onto the surface, altering reflectivity and color. Over time, accumulated layers modify thermal behavior by absorbing more solar energy. Such haze formation demonstrates how atmospheric chemistry, even when transient, can leave lasting imprints on surface evolution. Subtle variations in dwarf planet mass distribution can be detected through precise tracking of spacecraft trajectories. Slight deviations in velocity reveal gravitational anomalies linked to internal heterogeneity. These measurements allow scientists to infer core size, ice shell thickness, and possible liquid layers without direct sampling. Gravity mapping thus serves as a powerful diagnostic tool, transforming distant flybys into detailed internal portraits. In regions far from the Sun, solar tides still exert measurable influence on dwarf planet surfaces over immense timescales. These tides flex outer layers minutely, contributing to internal friction and heat generation. Though weak, such effects accumulate across billions of years, adding to the energy budget that sustains internal mobility. This slow influence underscores how even distant solar forces shape planetary evolution. Fragments produced by collisions involving dwarf planets can persist as coherent families with shared orbital characteristics. Identifying these families requires careful analysis of orbital elements and surface composition. Their existence confirms that large impacts occurred even in sparsely populated regions. Studying these remnants helps reconstruct violent episodes that redistributed mass and altered spin states across the outer solar system. Some dwarf planets display latitudinal banding in surface composition, driven by seasonal transport of volatile compounds. As sunlight migrates across hemispheres, frost accumulates preferentially at certain latitudes, leaving compositional stripes. These bands act as climate markers, preserving information about axial tilt and orbital eccentricity. Decoding them allows reconstruction of long-term environmental patterns beyond direct observation. Radiogenic heating within dwarf planets depends heavily on the initial abundance of radioactive isotopes. Worlds richer in rocky material retain more heat, prolonging internal activity. Comparing densities and compositions across different dwarf planets reveals how initial building blocks varied with distance from the Sun. This comparison refines models of early material sorting within the protoplanetary disk. Some dwarf planets possess escape velocities low enough that lighter molecules readily leave during warm periods. This selective loss alters atmospheric composition over time, enriching heavier gases. Traces of this fractionation appear in spectral data, offering insight into atmospheric evolution. Such gradual change highlights how even thin atmospheres undergo complex chemical histories, shaped by gravity and temperature. Ice mechanics on dwarf planets differ profoundly from terrestrial glaciers because of extreme cold and unique compositions. Nitrogen and methane ices flow at rates comparable to warm water ice on Earth, despite frigid conditions. Laboratory studies support these observations, confirming that molecular structure governs deformation behavior. These findings broaden understanding of solid-state physics under exotic planetary environments. Several dwarf planets exhibit evidence of past global expansion or contraction, inferred from widespread fracture networks. Expansion could result from internal freezing that increased volume, while contraction might follow cooling and compaction. Mapping these features reveals whether a body gained or lost internal heat over time. Such structural clues help determine long-term thermal trends. Rather than existing in isolation, dwarf planets interact with streams of charged particles from the Sun. These particles implant energy into surface materials, driving chemical reactions that darken and redden exposed areas. The rate of alteration depends on distance, magnetic shielding, and surface composition. By comparing coloration across objects, scientists estimate exposure durations and environmental conditions. Advancing telescope sensitivity has enabled detection of faint absorption features linked to rare compounds on dwarf planet surfaces. These detections refine compositional inventories and challenge assumptions about chemical simplicity. Each new molecule identified expands understanding of available building blocks in the outer solar system, informing theories about chemical evolution beyond the snow line. Some dwarf planets rotate synchronously with their moons, presenting the same face during each orbit. This locking alters surface evolution by fixing illumination patterns, creating permanent hemispheric contrasts. Over time, these contrasts become etched into terrain and composition. Studying such systems reveals how rotational dynamics influence planetary surfaces. Long-term stability of dwarf planet orbits depends on complex gravitational resonances that protect them from close encounters. These resonances act like invisible barriers, maintaining spacing and preventing chaotic scattering. Analyzing these relationships helps reconstruct the migration history of giant planets that established current orbital architecture. Evidence from surface chemistry suggests that cosmic rays penetrate only shallow depths on dwarf planets, leaving deeper layers relatively pristine. This shielding preserves ancient material beneath the surface, potentially accessible through future exploration. Such untouched layers could provide direct samples of early solar system matter. Ultimately, dwarf planets occupy a critical niche between minor bodies and full-fledged planets, embodying transitional states of planetary development. Their varied properties illustrate multiple evolutionary pathways shaped by environment, composition, and history. Studying them enriches understanding of planetary formation as a continuum rather than a set of rigid categories, revealing complexity where simplicity was once assumed. The surfaces of some dwarf planets are coated with frost layers that cycle between solid and gaseous states depending on orbital position, creating ephemeral atmospheres that vanish when temperatures drop. On Pluto, for instance, seasonal sublimation of nitrogen ice temporarily thickens the atmosphere before it refreezes, leaving intricate frost patterns across plains and craters. These cycles slowly redistribute surface material over decades or centuries, effectively breathing across the landscape. Observing these phenomena provides insight into how volatile compounds behave under extremely low pressure and temperature, revealing dynamic interactions between atmosphere, ice, and sunlight on distant, frigid worlds. Subsurface oceans on certain dwarf planets may harbor exotic chemistries due to the presence of salts, ammonia, or other anti-freezing agents. These compounds lower the melting point of water, allowing liquid layers to persist even under kilometers of ice at temperatures far below freezing. By modeling heat transfer from radioactive decay and tidal flexing, scientists estimate that these oceans could remain liquid for billions of years. The potential for chemical gradients within such layers raises questions about prebiotic chemistry, energy availability, and the extent to which isolated oceans might sustain molecular evolution in the outer solar system. The rotational axes of dwarf planets often experience chaotic shifts over geological time, resulting in extreme seasonal variations and uneven solar illumination. Such axial changes influence the distribution of volatile ices, shaping plains, mountains, and basins differently depending on which hemisphere receives prolonged sunlight. For worlds with elongated orbits, this creates multi-century climatic cycles that leave discernible patterns in surface morphology. By reconstructing these patterns, astronomers can infer long-term rotational behavior and climatic history, revealing how even small bodies undergo cycles of environmental transformation on scales far exceeding human experience. Some dwarf planets display an unusually high albedo contrast across their surfaces, reflecting regional differences in composition or age. Bright deposits of frozen nitrogen, methane, or water ice stand in stark contrast to darker, tholin-rich regions modified by radiation. These contrasts can persist for millions of years, allowing scientists to track resurfacing events, deposition patterns, and radiation effects over time. Comparing reflectivity across hemispheres offers a window into both external processes, like cosmic ray exposure, and internal activity, such as cryovolcanic resurfacing, illustrating the interplay between chemistry, geology, and environmental conditions on distant icy worlds. Impact craters on icy dwarf planets often reveal subsurface layers otherwise hidden from view. The depth and morphology of craters expose stratification in ice, mixed compounds, and brine deposits. Analyzing these features informs estimates of mechanical strength, layer composition, and thermal history. Some craters even show evidence of post-impact relaxation, where viscous ice slowly flows to smooth depressions. This ongoing adaptation demonstrates that these bodies are capable of adjusting to stress over extended periods, unlike smaller asteroids where such flow is negligible, offering unique insight into cryogeological mechanisms beyond the terrestrial experience. Variations in spectral signatures across dwarf planet surfaces suggest that solar ultraviolet radiation drives chemical evolution over eons. Simple ices transform into complex organics, including reddish tholins that coat plains, mountains, and crater interiors. This slow chemical modification alters surface reflectivity and color patterns, providing a visual record of radiation exposure. By analyzing these changes, astronomers reconstruct cumulative interactions between solar energy and surface chemistry, offering clues about long-term molecular stability and the evolution of organic compounds under frigid, low-pressure conditions in the outer solar system. Some dwarf planets harbor moons, whose orbital configurations indicate past catastrophic collisions. These satellites, often aligned in coplanar circular orbits, suggest they coalesced from ejected material rather than independent capture. Detailed study of their compositions and densities confirms a shared origin with the primary body. These systems allow reconstruction of ancient impacts that restructured mass, altered rotational periods, and redistributed angular momentum. Examining these remnants provides insight into the violent history of the outer solar system, highlighting the formative role of collisions in shaping both primary bodies and their smaller companions over billions of years. The shapes of dwarf planets provide clues to their internal constitution and rotational history. Bodies like Haumea demonstrate how rapid spin elongates a world into an ellipsoid, redistributing surface material along equatorial regions. This distortion influences gravity variations, fracture propagation, and the migration of volatiles, shaping landscape evolution. Understanding these effects allows scientists to reconstruct early rotational states and evaluate structural strength, revealing how angular momentum and internal rigidity interact to determine the observable physical form of distant icy objects. Even in extreme cold, dwarf planets exhibit cryovolcanic features formed by the eruption of liquid or slushy ices. Unlike molten rock volcanism, these eruptions involve water mixed with salts, ammonia, or other volatiles, which lower the freezing point and allow slow extrusion onto the surface. Such events resurface regions, smooth terrain, and deposit unique chemical signatures that persist for millions of years. Identifying these features provides a window into subsurface activity, confirming that internal heat, chemical layering, and gravity can drive geological change even on relatively small, distant planetary bodies. The interaction of dwarf planets with the solar wind produces measurable sputtering effects on surface materials. Charged particles gradually erode the outermost layers, releasing molecules into space and subtly altering composition over time. These interactions also generate transient exospheres, in which gases migrate briefly before freezing onto colder regions. Studying this phenomenon informs understanding of long-term surface evolution, volatile retention, and atmospheric escape, highlighting the delicate balance between environmental exposure and the preservation of primordial materials on remote, icy worlds. Subtle differences in bulk density among dwarf planets reveal distinct formation conditions and compositions. Lower density bodies indicate higher ice content, whereas higher density objects imply greater rock fraction. These disparities suggest variations in accretion location, temperature, and collisional history during the early solar system. By combining density measurements with orbital dynamics, scientists can infer migration patterns, the efficiency of accretion, and the distribution of primordial material across the outer solar system, building a clearer picture of planetary system evolution beyond the inner planets. Some dwarf planets exhibit longitudinal bands or regions of differing composition aligned with rotational axes, likely caused by long-term seasonal deposition of volatiles. As sunlight moves across hemispheres, ices migrate and settle preferentially, leaving chemical or reflectivity gradients. These bands provide a historical record of climatic cycles and orbital orientation, allowing astronomers to trace axial tilt variations and surface evolution over centuries. Observing and modeling these patterns yields insight into how orbital mechanics, sunlight exposure, and volatile chemistry interact to create persistent surface heterogeneity. The presence of ammonia, and other anti-freezing compounds in dwarf planet ices allows the maintenance of liquid layers beneath frozen exteriors. These solutes lower melting temperatures significantly, preventing complete solidification even under extreme cold. Subsurface liquids may facilitate slow chemical interactions and heat redistribution, preserving internal complexity despite diminutive size. Investigating these solutes provides critical context for understanding thermal evolution, internal dynamics, and the possibility of habitable niches in remote, frigid planetary bodies, otherwise considered inert or static. Dwarf planets located in resonant orbits maintain stability through long-term gravitational interactions with giant planets. These resonances prevent close approaches and collisions, preserving their positions over billions of years. The resulting orbital regularity allows for predictable cycles of sunlight exposure, volatile migration, and surface evolution. By studying these resonance effects, scientists reconstruct the influence of massive neighbors on small icy worlds, revealing how gravitational choreography governs both motion and environmental conditions in the outer solar system. Surface coloration on distant dwarf planets can indicate historical exposure to cosmic rays, ultraviolet light, and charged particles. Areas of darker material often contain radiation-processed organics, while brighter regions reflect fresher deposits. Mapping these variations provides insight into resurfacing events, surface ages, and exposure history. Such observations reveal the cumulative impact of environmental energy over eons, demonstrating how remote worlds record the subtle interplay of radiation, chemistry, and geological activity in ways that preserve ancient solar system history. Some dwarf planets rotate asynchronously with their moons, producing unique tidal interactions that slowly influence internal structure and rotational dynamics. Over millions of years, these effects can generate heat sufficient to drive minor geological activity, reshape subsurface layers, and alter orbital parameters. Even modest tidal influences highlight the interconnectedness of satellites and their primary bodies, offering a mechanism for maintaining internal energy and surface modification in worlds far too small to retain heat through radioactive decay alone. Ice tectonics, evidenced by long fractures and ridges, has reshaped the surfaces of certain dwarf planets, reflecting internal stresses and volumetric changes. Expansion and contraction of frozen material, coupled with rotational forces, produces terrain unlike anything found on rocky planets. Studying these features allows researchers to infer the distribution of subsurface ice, thermal gradients, and past episodes of internal activity. Such tectonics demonstrates that small, cold bodies can exhibit structural evolution comparable in complexity to that of much larger terrestrial planets. Transient atmospheres can form when ices sublimate at perihelion, only to refreeze as the dwarf planet moves farther from the Sun. This cyclical behavior redistributes material, sculpting plains, craters, and mountains over decades or centuries. The temporary presence of gases affects surface chemistry, insulation, and reflectivity, leaving lasting imprints even after freezing resumes. Observing these cycles offers a rare view into dynamic planetary phenomena operating at extreme distances from the Sun, where low temperatures and weak gravity dominate environmental conditions. Remote sensing reveals that some dwarf planets contain complex hydrocarbons layered above simpler ices, forming a stratified chemical architecture. Radiation modifies upper layers more rapidly, while underlying ices remain largely pristine. This vertical differentiation provides insight into exposure history, chemical stability, and environmental interactions. By modeling these layered compositions, scientists understand how external forces shape chemical evolution over billions of years, producing surfaces that serve as natural archives of solar and cosmic influence. Even at immense distances, the Sun exerts enough influence to drive subtle surface migration of volatile ices on dwarf planets. Differential heating causes gases to sublime and recondense in colder regions, gradually smoothing plains or forming localized deposits. These mechanisms create evolving topography and chemical distribution despite the extremely low energy environment. Studying these processes illuminates how energy input, however minimal, can produce measurable change over geologic timescales, challenging assumptions about inactivity on remote, icy worlds. The presence of tiny craters and microfractures provides evidence that dwarf planets remain exposed to slow but persistent bombardment by meteoroids. These small impacts stir surface material, reveal subsurface ices, and trigger localized stress responses. Over millions of years, this continuous exposure contributes to the renewal of surface features and to the mixing of chemical layers. Tracking impact frequency and distribution helps reconstruct the flux of material in the outer solar system, linking distant planetary surfaces to broader dynamical evolution. Some dwarf planets exhibit extreme axial tilts that produce unusual seasonal cycles, with poles alternating between months of near-constant sunlight and prolonged darkness. This creates dramatic redistribution of volatiles across the surface, forming frost accumulations in shadowed regions while exposed areas lose material to sublimation. Over millennia, these cycles sculpt hemispheric asymmetries in reflectivity and composition. Understanding how axial tilt influences surface evolution provides insight into climate behavior far from the Sun, revealing that even distant icy worlds experience complex environmental changes driven by orbital mechanics and solar energy gradients rather than tectonics or atmospheric pressure. Subtle ridges on dwarf planet surfaces indicate internal contraction or expansion as ice layers respond to thermal variations. These features can stretch for hundreds of kilometers and suggest that the internal structure retains flexibility despite frigid temperatures. By studying ridge orientation and distribution, researchers infer thermal history, ice shell thickness, and the presence of subsurface anomalies such as brine pockets or weak layers. Such analysis demonstrates that even small distant worlds undergo mechanical adjustments that shape large-scale topography, offering clues about long-term stability, energy transport, and the interaction between internal and surface dynamics across geologic time. Remote spectral observations reveal that certain dwarf planets contain methanol ice within craters and depressions, a compound that stabilizes other volatile ices and slows sublimation. The presence of methanol provides insight into chemical preservation in extremely cold environments, suggesting that layered ices can retain original solar system material for billions of years. Methanol also contributes to surface coloration, giving regions a subtle reddish hue when exposed to radiation. Detecting these compounds informs models of outer solar system chemistry and illustrates how minor chemical variations influence long-term stability, surface reflectivity, and the evolution of icy landscapes in remote planetary bodies. Occasionally, dwarf planets display faint but measurable thermal emissions that betray subsurface heat flow. These emissions, often detected in infrared wavelengths, indicate that radioactive decay and residual heat from formation still warm the interior. Even minimal warming can influence ice flow, surface renewal, and retention of subsurface liquids. By mapping these thermal anomalies, astronomers gain insight into internal composition, insulation properties, and potential cryovolcanic activity. Such subtle signatures underscore the fact that planetary-scale thermodynamics operate even on small, distant bodies, revealing ongoing dynamism where once static, frozen landscapes were assumed to dominate. Surface pits and depressions on dwarf planets often form through sublimation collapse, where volatile ices transition directly to gas, leaving cavities in the crust. These pits can cluster in patterns indicating localized concentration of specific compounds or structural weaknesses. Over time, they coalesce or deepen, modifying the surface in recognizable ways. Studying these formations helps reconstruct the chemical makeup, temperature fluctuations, and structural integrity of icy layers. Additionally, these features provide insight into how low-gravity, frigid worlds can undergo morphological evolution driven by phase changes, demonstrating that even distant planetary surfaces are shaped by chemical, thermal, and mechanical factors over geologic timescales. Evidence from high-resolution imaging indicates that certain dwarf planets have regions resembling polygonal terrain, likely formed by slow contraction and expansion of icy layers. These polygons reveal underlying thermal stresses and mechanical properties of the crust, reflecting both composition and age. Their size, orientation, and distribution allow scientists to infer internal viscosity, freezing behavior, and long-term stability. Such terrain demonstrates that even in extremely cold, low-pressure environments, material can undergo large-scale structural adjustment. The resulting patterns are not random, but encode a history of environmental cycles, internal dynamics, and mechanical responses that provide a tangible record of planetary evolution far from the Sun. Some dwarf planets interact gravitationally with distant objects in resonant chains, creating subtle but persistent orbital patterns. These resonances prevent close encounters and collisions, preserving structural integrity and stabilizing orbital paths over billions of years. The resulting arrangement offers insight into the early migration of giant planets and the sculpting of the outer solar system. Observing these orbital relationships allows astronomers to model gravitational influences that extend far beyond the visible surface, highlighting the interplay between dynamics and morphology in shaping the environment of small, remote worlds over cosmic timescales. Chemical heterogeneity across the surfaces of dwarf planets often arises from migration of ices and deposition of radiation-processed organics. Brighter regions indicate freshly exposed material, while darker areas result from prolonged exposure to cosmic rays and ultraviolet light. The juxtaposition of colors, coupled with terrain analysis, provides a historical record of resurfacing events, impact exposure, and chemical evolution. By decoding these patterns, scientists can determine relative ages of surface regions, identify areas of active or past geological activity, and understand how solar energy, radiation, and chemical composition interact to produce the complex, visually striking surfaces observed on icy outer solar system bodies. Some dwarf planets retain tiny, irregular moons that may have formed from captured debris rather than collisions. These satellites often have chaotic orbits influenced by both the primary body and solar gravitational forces. Their presence provides indirect evidence of past interactions and perturbations, offering clues about the mass, density, and collisional history of the parent dwarf planet. By analyzing the motion and composition of these small companions, scientists reconstruct episodes of capture, ejection, or collisional fragmentation, enriching the understanding of how minor planetary systems evolve and interact with surrounding populations of icy bodies in the outer solar system. Unique surface features on dwarf planets sometimes include streaks and grooves aligned with prevailing winds or sublimation flows in past epochs. While current atmospheres are often too thin for significant wind activity, historical sublimation and minor transient gases can mobilize material, leaving linear patterns. These markings preserve information about orientation, surface slopes, and volatile distribution, acting as geological fossils of environmental interactions. By examining such features, researchers gain insight into the subtle forces shaping surface morphology, including frost transport, ice sublimation, and long-term environmental variation, highlighting that even remote worlds record the cumulative effect of seemingly negligible forces over eons. Internal differentiation in dwarf planets occurs when heavier rock sinks toward the core, while lighter ices rise, producing layered structures that influence gravitational fields and surface expression. This stratification affects spin dynamics, tectonic stresses, and cryovolcanic potential. Evidence of differentiation can be inferred from mass measurements, rotation rates, and surface features, offering clues to thermal history and composition. Understanding how these layers interact provides a model for how small bodies transition from homogeneous accretions into complex worlds with distinct internal zones, demonstrating that planetary complexity does not require massive size, but can emerge from chemistry, gravity, and thermal evolution. Localized bright patches on dwarf planets often indicate recent exposure of fresh ices, either through impact excavation or internal activity. These regions reflect sunlight more efficiently than surrounding terrain, creating temporary visual contrasts. Monitoring their persistence provides insight into erosion rates, volatile sublimation, and surface renewal. Bright spots may also reveal compositional differences, highlighting areas where nitrogen, methane, or water ice is particularly abundant. Such observations inform models of energy balance, resurfacing mechanisms, and long-term chemical evolution, illustrating that even small remote bodies exhibit episodic activity capable of reshaping their visible surfaces. Spectroscopic studies reveal that some dwarf planets possess complex hydrocarbons on their surfaces, resulting from the photochemical transformation of simpler ices. These compounds accumulate over millions of years, darkening terrain and contributing to reddish or brownish hues. They also serve as tracers for radiation exposure and environmental history, allowing scientists to track long-term chemical interactions in extreme conditions. By comparing spectral data across objects, researchers gain insight into outer solar system chemistry, molecular evolution, and the interplay between radiation, volatile migration, and surface composition, demonstrating how distant, cold worlds retain rich chemical histories that rival larger planets. The rotational periods of dwarf planets can vary widely, from hours to several days, significantly influencing surface behavior and energy distribution. Rapid rotation flattens equatorial regions, modifies gravitational gradients, and affects how ices migrate. Slower rotation creates longer exposure cycles for sunlight on specific regions, enhancing thermal contrasts and volatile redistribution. By analyzing rotational patterns in conjunction with surface features, scientists can infer past impacts, internal structure, and energy distribution, providing a framework to understand how spin dynamics affect surface morphology, seasonal cycles, and the long-term evolution of remote, icy planetary bodies. Transient exospheres on some dwarf planets form as volatile sublimate during perihelion, creating ephemeral layers of gas. These layers redistribute surface ices, carry chemical species to new regions, and interact with solar wind particles before freezing back onto the crust. Monitoring these temporary atmospheres provides insight into volatile cycling, surface renewal, and potential chemical reactions, illustrating that even the smallest, coldest worlds can maintain active surface-atmosphere interactions. Such phenomena highlight the delicate interplay of temperature, gravity, and solar energy in shaping distant planetary environments over geologic timescales. Many dwarf planets display subtle evidence of past collisions that restructured surfaces without complete disruption. Impact ejecta deposits create uneven terrains, alter local albedo, and occasionally form minor satellite systems. Analyzing crater density, size distribution, and ejecta patterns allows reconstruction of collision energies, angles, and subsequent evolution of the body. These observations reveal a dynamic outer solar system where impacts contributed to internal heating, spin changes, and surface modification. By studying collision evidence, scientists gain a broader understanding of the mechanical history of icy, distant worlds and the forces that shaped their current morphology and rotational dynamics. Some dwarf planets exhibit crater chains that stretch across vast stretches of their icy surfaces, often formed when fragments from a larger body broke apart before impact. These linear alignments reveal information about the trajectory, size, and velocity of incoming debris, as well as the mechanical response of the surface to repeated strikes. Crater chains sometimes expose subsurface material, offering a glimpse into composition and layering, while also acting as chronological markers that allow scientists to estimate relative surface ages. The patterns preserve a visual record of bombardment dynamics in the outer solar system over billions of years. Dark streaks on icy plains indicate localized deposits of radiation-altered organics, often concentrated along slopes or depressions. These streaks contrast sharply with surrounding reflective ice, highlighting the long-term interaction between surface chemistry and cosmic radiation. By measuring the distribution, thickness, and composition of these deposits, researchers infer exposure history, the stability of volatile compounds, and the mobility of surface material under extremely low temperatures. The streaks serve as natural archives, recording cumulative environmental effects, subtle sublimation flows, and past episodes of deposition, emphasizing that even small, distant worlds host complex chemical and geological narratives preserved over immense timescales. Subsurface radar studies suggest that some dwarf planets may harbor layered structures composed of alternating ice and silicate-rich materials. These layers affect thermal conductivity, mechanical strength, and the propagation of internal stresses, influencing surface fracture patterns. By modeling radar reflections and density variations, scientists deduce the thickness, composition, and continuity of these strata, revealing a hidden structural complexity otherwise invisible from optical observations. Such stratification implies a history of accretion, differentiation, and compaction that extends beyond superficial features, highlighting how distant icy bodies possess intricate internal architectures shaped by primordial formation conditions and subsequent evolution over billions of years. Transient geysers have been hypothesized on certain dwarf planets, erupting small jets of nitrogen, methane, or water vapor under episodic heating conditions. These eruptions modify local terrain, deposit fresh ices, and create temporary plumes that may interact with solar radiation to form complex molecules. Although weak compared to terrestrial volcanism, the phenomenon demonstrates that internal heat and subsurface reservoirs can mobilize materials even on small, frigid worlds. Studying potential geyser activity provides insight into internal temperature profiles, volatile abundance, and structural weaknesses, offering a window into dynamic surface-atmosphere interactions in regions of the solar system previously assumed to be geologically inert. Longitudinal studies of reflectivity on dwarf planets reveal seasonal migration of frost deposits, forming alternating bright and dark bands that persist over decades. These patterns indicate the movement of nitrogen, methane, and carbon monoxide ices across latitudes as the planet approaches or recedes from the Sun. Tracking these bands allows reconstruction of axial tilt, orbital eccentricity, and environmental cycles, offering insight into long-term climate variations. Observing frost migration demonstrates that even distant objects experience ongoing modification of surface chemistry and albedo, emphasizing how minimal solar input can drive measurable changes in landscape appearance and material redistribution across extremely cold planetary surfaces. High-resolution imaging of certain dwarf planets has revealed pit chains and collapse features formed by sublimation of subsurface ices. When volatile rich layers vaporize, they leave cavities that gradually coalesce into irregular depressions, sometimes aligned with structural weaknesses. These features provide information about the depth, composition, and mechanical behavior of underlying layers, while also recording past thermal and environmental conditions. Over millions of years, pit formation reshapes plains, alters local reflectivity, and exposes fresher material. Studying these phenomena allows scientists to reconstruct chemical and structural evolution, illustrating how even small, cold bodies undergo complex morphological changes driven by the interplay of temperature, composition, and gravity. Some dwarf planets exhibit unusually high density contrasts between core and mantle, suggesting a history of differentiation influenced by accretion and radioactive heating. These contrasts affect gravity fields, rotational dynamics, and tectonic stress distribution. By combining mass measurements, shape modeling, and rotational analysis, scientists infer the degree of internal stratification, core composition, and ice layer thickness. Understanding density variation provides insight into formation conditions, collisional history, and thermal evolution. Even modest differences in internal composition influence surface morphology, fracture development, and potential cryovolcanic activity, revealing that small remote bodies can evolve highly structured interiors similar to larger planetary analogues. Evidence of axial precession on dwarf planets indicates that their rotational axes gradually shift over millions of years, altering patterns of sunlight exposure and ice migration. This slow wobble affects seasonal deposition and sublimation cycles, producing hemispheric asymmetries in surface composition and reflectivity. By analyzing frost distribution, crater illumination, and terrain modification, researchers infer the magnitude and timing of these axial changes. Such long-term dynamical variations reveal that even distant, low-mass objects are subject to complex rotational mechanics that shape climate, volatile behavior, and geological features over extended timescales, illustrating how orbital and rotational forces interplay with surface evolution. Surface pits on certain dwarf planets often exhibit concentric layering, hinting at episodic deposition of ices and organic compounds. These layers accumulate as gases condense during cold phases and sublimate in warmer intervals, creating stratified crusts that preserve environmental history. Examining the composition and thickness of these layers allows scientists to reconstruct past climatic cycles, volatile abundance, and radiation exposure. Layered pits also provide insight into the mechanics of ice flow and subsurface structure, revealing how repetitive chemical and thermal interactions shape terrain over billions of years. Such formations act as natural archives of long-term planetary evolution in extreme outer solar system conditions. Tidal interactions with small satellites can induce flexing in dwarf planet crusts, generating heat and subtle surface stress. Even modest tidal forces influence internal energy budgets, potentially sustaining cryovolcanic activity or reshaping surface ice. The alignment, eccentricity, and mass of satellites determine the magnitude of tidal effects, allowing scientists to model internal responses based on observed surface deformation. This mechanism demonstrates that distant, low-mass bodies can experience ongoing internal modification, providing energy sources that maintain geologic activity and influence surface evolution, despite extreme cold and limited solar input, illustrating how gravitational relationships shape the long-term dynamism of remote planetary systems. Some dwarf planets reveal ancient fractures that cut across their surfaces, tracing stress lines formed during cooling and contraction of icy crusts. These linear features often intersect with craters and ridges, recording a complex history of internal and external forces. By examining the orientation, depth, and spacing of fractures, scientists infer ice viscosity, thermal gradients, and episodic stress events over billions of years. Such structural evidence highlights that small, distant worlds are capable of sustaining long-term mechanical deformation, producing topographical diversity that encodes both ancient formation conditions and ongoing responses to subtle internal and orbital dynamics. Bright reflective spots occasionally appear in depressions or crater floors, suggesting the presence of recently exposed volatile ices like nitrogen, methane, or carbon monoxide. These deposits contrast sharply with surrounding darker, irradiated terrain and may originate from minor sublimation-driven eruptions, impact excavation, or internal activity. Monitoring their evolution reveals rates of volatile sublimation, frost migration, and surface renewal, offering insight into seasonal and long-term chemical cycles. Bright spots also provide clues about internal reservoirs and thermal conditions, demonstrating that even remote small bodies can maintain dynamic interactions between subsurface materials and surface environments, producing localized landscapes of striking optical and chemical variation. Spectral mapping indicates that some dwarf planets contain regions rich in complex tholins, created by the interaction of ultraviolet light and cosmic rays with simpler ices. These reddish to brownish deposits accumulate over eons, darkening surfaces and forming chemical gradients that record exposure. History. Variation in tholin thickness and distribution reflects both irradiation levels and the mobility of underlying ices. By analyzing these patterns, researchers reconstruct long-term chemical evolution, assess surface age, and infer past environmental conditions. Tholins serve as natural markers of radiation chemistry, showing how energy from distant sunlight and cosmic sources transforms initially simple molecules into complex, enduring compounds. Small, irregular moons around dwarf planets often display synchronous rotation, with the same face always pointing toward the parent body. This alignment results from tidal locking over millions of years, altering orbital energy and contributing to internal heating. Studying the shape, composition, and orbital behavior of these moons provides clues about the formation and collisional history of the parent dwarf planet, including potential past disruptions or fragmentary accretion events. These miniature companions act as natural probes, revealing gravitational interactions, material composition, and dynamical evolution in ways that illuminate the broader architecture of the outer solar system. Some dwarf planets exhibit polygonal or cellular terrain patterns, likely resulting from the slow contraction and expansion of surface ices. These geometric features often span kilometers and reveal the mechanical properties of crustal layers, including ice viscosity and fracture behavior. The presence, size, and orientation of polygons allow scientists to model thermal history, surface stresses, and potential subsurface liquid pockets. Observing polygonal terrains underscores that even extremely cold, low-pressure worlds can undergo large-scale structural rearrangement. Each cell preserves a subtle record of geophysical activity, linking mechanical responses to environmental cycles over millions or billions of years. Volatile migration on dwarf planets can create ephemeral frost layers that advance across plains, craters, and slopes depending on temperature gradients. As nitrogen, methane, and carbon monoxide sublimates in sunlight and recondenses in shadowed regions, surface composition shifts subtly over decades. These slow transformations sculpt albedo patterns, influence thermal conductivity, and record seasonal extremes, dictated by orbital eccentricity and axial tilt. Studying these migratory patterns provides insight into climate cycles, chemical behavior of ices under low pressure, and energy distribution across planetary surfaces. Such phenomena demonstrate that even distant frozen worlds experience dynamic modification driven by minimal but persistent solar input. Cratered terrains on dwarf planets often reveal secondary features such as ejecta rays, fractures, and subtle topographical undulations. The morphology and composition of these secondary structures indicate impact energy, target material, and post-impact surface relaxation. Craters can expose subsurface ices, revealing stratification or brine layers otherwise hidden beneath hardened crusts. Comparing crater distribution and morphology across hemispheres allows scientists to infer relative surface ages, resurfacing events, and impactor flux in the outer solar system. This analysis emphasizes that even seemingly inert surfaces retain rich evidence of collisional history, structural heterogeneity, and chemical layering shaped over billions of years. Thermal infrared measurements show that some dwarf planets emit slight heat signatures, reflecting residual internal warmth from radioactive decay and primordial accretion. This subtle energy influences ice flow, minor tectonic movement, and the maintenance of subsurface liquid layers. Mapping these emissions enables scientists to assess internal composition, insulation properties, and potential cryovolcanic activity. Even minimal heat output can drive measurable change in surface morphology and volatile behavior over geological timescales, demonstrating that small, frigid bodies remain internally active despite extreme distance from the Sun. Thermal mapping thus offers a window into hidden dynamics beneath frozen exteriors. Polygonal pits on certain dwarf planets provide evidence for cyclical sublimation and deposition of volatile ices, forming stratified walls and layered floors. These structures act as geological timekeepers, recording repeated episodes of frost accumulation and vapor loss. Studying their dimensions, orientation, and internal composition allows scientists to infer thermal history, mechanical properties, and chemical evolution. Such pits demonstrate that low-gravity environments permit complex terrain development, driven by minor phase changes in volatile substances. Even in the far reaches of the solar system, these formations showcase how subtle environmental interactions over eons can produce intricate and enduring surface features. Long-term monitoring of dwarf planets reveals that rotational periods can vary slightly over millennia due to tidal interactions with moons or distant gravitational influences. These variations affect the distribution of sunlight, ice migration, and temperature gradients across the surface. Modeling rotational shifts allows reconstruction of historical climate cycles, axial tilt changes, and energy redistribution, offering insight into the subtle ways orbital and rotational dynamics shape environmental conditions. Even minor changes in spin can leave enduring marks on surface morphology and volatile placement, illustrating that the complex interplay of rotation, gravity, and orbital mechanics drives continuous evolution on these small remote worlds. Subsurface modeling suggests that some dwarf planets may host pockets of briny liquid beneath icy crusts, maintained by a combination of internal heat and antifreeze-like solutes. These reservoirs, though limited in scale, influence surface geology by softening ice layers, enabling minor tectonic flexing and potentially feeding transient cryovolcanic activity. Detection relies on gravity measurements, surface deformation analysis, and thermal modeling, providing indirect yet compelling evidence for hidden complexity. The existence of such brines demonstrates that even small, distant bodies retain localized zones capable of sustaining chemical mobility, phase transitions, and geological renewal despite extreme temperatures and minimal solar energy. Craters filled with bright reflective deposits often indicate the slow accumulation of volatiles that migrate from surrounding terrain. These deposits can reveal relative ages, with fresher material reflecting sunlight more efficiently than older, radiation-darkened surfaces. By examining the composition, thickness, and pattern of bright crater fills, scientists reconstruct cycles of frost migration, seasonal sublimation, and chemical layering. Observations across multiple dwarf planets suggest that such features are widespread, highlighting that even small, frozen bodies record dynamic interactions between surface and environment. These luminous regions also offer windows into internal volatile availability and the subtle forces shaping morphology over geologic time. Some dwarf planets display linear grooves and ridges formed by crustal extension or contraction, often stretching for hundreds of kilometers. These features trace structural stresses induced by cooling, internal differentiation, or tidal interactions with nearby satellites. The orientation and distribution of grooves provide clues about crustal thickness, ice rheology, and historical thermal gradients. In certain cases, these linear features intersect older terrains, preserving a chronological sequence of stress events. Such evidence emphasizes that distant icy worlds experience mechanical deformation despite their small size and low gravity. Studying these ridges allows scientists to reconstruct tectonic histories and assess the long-term evolution of outer solar system bodies. Observation of tiny satellites reveals that their irregular shapes often reflect a collisional origin, resulting from fragments captured after past impacts. Their eccentric orbits and rotational characteristics serve as indicators of gravitational evolution, tidal interactions, and dynamical stability. Analysis of their composition provides complementary insight into the parent dwarf planet's material, allowing reconstruction of formation events and subsequent interactions. These miniature companions are natural laboratories for understanding orbital mechanics, the efficiency of debris capture, and the role of small satellites in shaping surface stress on primary bodies. Their presence illustrates that even minor systems retain echoes of ancient solar system events. Spectral analysis shows that some dwarf planets possess trace ammonia hydrates, which modify the thermal and mechanical properties of surface ices. Ammonia lowers the freezing point of water, enabling partial melting and facilitating surface mobility at temperatures otherwise prohibitive for ice flow. Its detection offers clues to chemical evolution, internal composition, and the potential for past cryovolcanic activity. Mapping ammonia-rich regions allows scientists to connect surface features such as ridges, pits, or domes with underlying chemistry. Even in extreme cold and low-pressure environments, the presence of minor chemical constituents demonstrates how complex interactions among volatiles shape geology, influence energy transfer, and maintain localized dynamism. Some dwarf planets exhibit faint, transient atmospheres composed of sublimated nitrogen, methane, or carbon monoxide, detectable only near perihelion. These ephemeral layers redistribute surface ices, interact with solar radiation, and occasionally produce minor winds capable of moving fine particles. Studying their composition and seasonal variation provides insight into volatile cycling, sublimation, rates, and environmental response to orbital eccentricity. Such fleeting exospheres demonstrate that even small, distant worlds maintain subtle exchanges between surface and surrounding space. These cycles influence reflectivity, chemical deposition, and surface renewal, showing that planetary evolution is driven not only by impacts and internal activity, but also by transient, solar-induced atmospheric phenomena. Complex crater chains on dwarf planets often indicate fragmentation of impacting bodies before surface contact. Their alignment and spacing preserve records of trajectory, velocity, and angle of approach, offering insight into the bombardment history of the outer solar system. Detailed study of these chains can reveal surface composition by exposing subsurface layers, highlighting stratification, or chemical anomalies. The interaction between impactor energy and low gravity, icy surfaces creates unique morphological signatures distinct from larger terrestrial planets. Such evidence provides a rich archive of collisional dynamics, demonstrating that even small, cold worlds retain lasting imprints of gravitational encounters and extraterrestrial impacts over billions of years. Surface albedo variations on dwarf planets often result from the interplay between radiation-darkened organics and freshly deposited volatiles. Darkened regions may be enriched in tholins, formed by long-term ultraviolet and cosmic ray exposure, while lighter areas correspond to more recently exposed ices. Observing these contrasts allows reconstruction of resurfacing events, relative terrain age, and chemical heterogeneity. Albedo mapping also informs thermal models, since reflective and absorbent surfaces respond differently to sunlight, influencing sublimation and ice migration. Such subtle contrasts reveal that even in the far reaches of the solar system, surface chemistry and energy dynamics are actively shaping landscapes over time, scales spanning millions or billions of years. Subtle flexing in icy crusts may occur due to tidal interactions with distant satellites or neighboring objects, generating stress fractures or minor surface uplift. These mechanical responses can activate weak layers, mobilize ices, and subtly influence ridge or polygon formation. By measuring displacement, orientation, and correlation with orbital configurations, scientists infer internal strength, ice viscosity, and energy dissipation. Even minor tidal flexing provides a mechanism for localized geological activity in regions lacking substantial atmospheres or internal heat. This phenomenon demonstrates that gravitational interactions extend far beyond large moons and planets, shaping terrain, surface evolution, and mechanical behavior on remote dwarf planets. Thermal modeling indicates that differential heating of surface ices can create micro-scale sublimation vents, where localized pockets of gas escape through cracks or porous layers. These vents subtly modify surrounding terrain by displacing material, concentrating bright ices, or creating faint streaks along slopes. Although small in magnitude, these interactions cumulatively alter albedo, surface roughness, and volatile distribution. Investigating vent locations and activity provides insight into thermal gradients, ice composition, and subsurface permeability. Such subtle yet persistent activity illustrates that even the coldest, most distant bodies in the solar system maintain ongoing surface modification, driven by energy variations on scales imperceptible to casual observation. Bright streaks observed along crater rims suggest recent exposure of volatile rich layers, potentially triggered by minor impacts or sublimation-driven material movement. These streaks often differ chemically from surrounding terrain, highlighting localized concentration of nitrogen, methane, or carbon monoxide ices. By tracking their evolution, researchers can determine rates of sublimation, frost migration, and surface renewal. Such features reveal that even distant, frozen worlds retain episodic activity that redistributes material across small scales, influencing albedo contrasts, thermal behavior, and chemical composition. The observation of these ephemeral streaks provides a dynamic perspective on surface evolution in environments once assumed to be entirely inert. Polygonal terrain visible on some dwarf planets indicates large-scale cracking of the icy crust, likely caused by slow expansion and contraction cycles. These geometric patterns often display regular spacing and can extend for kilometers, offering clues to thermal history, crustal thickness, and mechanical properties of underlying layers. Studying polygons provides insight into stress distribution, past temperature fluctuations, and potential subsurface mobility, revealing that even small remote worlds experience internal and surface deformation over billions of years. Each polygon encodes information about historical ice behavior, environmental conditions, and the subtle forces that have shaped the exterior of these distant planetary bodies. Observations suggest that certain dwarf planets retain thin exospheres during periods of increased solar proximity, composed primarily of sublimated nitrogen and methane. These transient atmospheres interact with surface ices, transporting volatiles from sunlit to shadowed regions. Although temporary and extremely tenuous, they drive localized chemical redistribution, subtle frost deposition, and minor erosion along slopes. Studying these ephemeral layers helps scientists understand volatile cycling, surface-atmosphere interactions, and the influence of orbital eccentricity on environmental variation. Even minimal atmospheric activity demonstrates that frozen worlds far from the Sun can sustain dynamic surface interactions, subtly modifying appearance and chemical composition over time. Subsurface differentiation in dwarf planets results in dense rock sinking toward the core, while lighter ices form outer layers, producing complex internal structure despite small size. This stratification influences gravitational fields, rotational dynamics, and the development of tectonic stresses. Evidence for differentiation is inferred from mass measurements, surface deformation, and rotational behavior, revealing variations in crust thickness and core composition. Understanding internal layering provides clues to thermal history, radiogenic heating, and the potential for cryovolcanic activity. Even modest internal differentiation can drive observable surface changes, showing that planetary complexity emerges not solely from size, but from chemical, thermal, and gravitational interactions acting over billions of years. Observations of faint surface pits suggest that localized sublimation of volatile ices drives the formation of depressions on dwarf planets. These features often cluster in patterns aligned with structural weaknesses or previous impacts. Over time, pits deepen and coalesce, exposing subsurface material while modifying albedo and microtopography. Analysis of pit distribution and morphology provides insight into ice composition, thermal fluctuations, and mechanical behavior of crustal layers. These subtle yet persistent changes demonstrate that even the coldest, low-gravity worlds experience surface evolution driven by phase changes, illustrating the ongoing interplay of chemical, mechanical, and thermal factors on distant planetary bodies. Tidal interactions with minor satellites produce measurable flexing of dwarf planet crusts, generating stress fractures and slight elevation changes. These mechanical effects can mobilize subsurface ices, modify ridge systems, and influence polygon formation. By modeling tidal forces, orbital eccentricity, and satellite mass, scientists can infer internal ice rheology and energy dissipation rates. Even limited tidal heating contributes to geological activity on otherwise frozen remote worlds, illustrating that gravitational forces extend beyond the largest planets and moons. Understanding these interactions highlights how the presence of companions subtly shapes terrain, alters stress patterns, and maintains localized geophysical activity over geological timescales. Thermal gradients across crater walls drive small-scale sublimation vents that release nitrogen or methane vapor, subtly reshaping surrounding terrain. These vents create faint streaks along slopes, concentrate bright ices, and influence local albedo, leaving signatures of energy redistribution visible over decades. Studying these features allows scientists to reconstruct temperature differences, ice composition, and the mobility of subsurface layers. Even minimal vent activity contributes to cumulative surface evolution, demonstrating that distant, cold worlds are not entirely static. Such micro-scale geological interactions reveal how thermal energy, ice chemistry, and low gravity collaborate to create enduring yet subtle alterations on planetary surfaces. High-resolution imaging has revealed longitudinal grooves on icy plains, likely formed by contraction, expansion, or internal stress redistribution. These linear depressions and ridges stretch for hundreds of kilometers, intersecting older terrain and recording sequential geological events. Analyzing their orientation, spacing, and morphology provides insight into mechanical properties, ice flow behavior, and thermal history. The existence of these grooves demonstrates that even small low-gravity worlds undergo large-scale structural adjustments over geologic time. Such features preserve a record of environmental and internal changes, offering a window into how distant dwarf planets respond mechanically to thermal, tidal, and compositional influences throughout their evolutionary history. As our journey through the distant realm of dwarf planets comes to a close, allow yourself to sink even deeper into rest. Let a sense of ease spread through your body and mind. Feel your thoughts gradually thinning, your muscles loosening, and your breath settling into its natural rhythm. Remain here, fully supported in this serene and steady space. If you enjoyed this relaxing moment, please consider leaving a like, subscribing, or sharing your thoughts below. Your support is deeply appreciated and helps others find their way to this peaceful space. You can also turn on the notification so you don't miss any of our future journeys together. But for now, let your body relax, release any tension, and allow your mind to drift. Good night and sleep well.